This video is going to run through operations with functions, including compositions of functions. So let's just start by doing an example. For the following functions, f of x equals x squared minus 3x, and g of x equals 5 minus x, find the following, state the domain of each. So before we get started, I'd like to note that we're working with a polynomial. F of x equal x squared minus 3x is a quadratic function. And then g of x equals 5 minus x is a linear function. Both of these functions have domains that are all real numbers. We can plug anything we want in for x. We'll never get an undefined or an error. All right, so now let's run through our operations. Let's start with f plus g. That's just asking us to add the two functions. So all we have to do is take x squared minus 3x plus 5 minus x. To add, we can combine like terms. So that gives me x squared minus 4x plus 5. This is also a polynomial. The sum of these two functions is another quadratic function. There's no denominators, there's no square roots. The domain of this is all real numbers. And in fact, when you add two functions, the domain of the sum is the domain of those two functions. The same is true when you subtract two functions. And let's see how that works next. F minus g, we're going to take x squared minus 3x and subtract 5 minus x. The only thing we have to watch out for is when we're subtracting, make sure that subtraction or that negative applies to both terms in that second function. So this becomes x squared minus 3x minus 5 plus x. Then we can combine like terms to get our final answer, x squared minus 2x minus 5. Once again, we now have a polynomial, technically a quadratic function, something with an x squared. It has a domain of all real numbers. We can plug anything in for x. All right, next one is f times g. F times g just means we're going to multiply the two functions together. So if we're going to take x squared minus 3x times 5 minus x, we can use that FOIL acronym to help us remember how to distribute. So we're going to take first x squared times 5, that's 5x squared. Outer, x squared times minus x gives me minus x to the third. Inner, minus 15x, and last, plus 3x squared. Once again, we can combine like terms. This becomes negative x to the third, plus 8x squared, minus 15x. This is another polynomial. My domain is all real numbers. All right, so when you are adding, subtracting, or multiplying two functions together, the domain of the result will always include the domain of your two functions. Since we were working with functions whose domains were all real numbers, if we add, subtract, or multiply those functions, the domain is still going to be all real numbers. All right, well, what about division? So if we want to take f divided by g, we have to take x squared minus 3x divided by 5 minus x. Now, there really isn't much we can do in terms of simplifying this, so I'm going to leave that just as is. There's no common factors. Yeah, we'll just leave that. That is our quotient right there. Okay, what about the domain? Now, when you divide functions, that all of a sudden might modify your domain, because now we have a denominator, and division by 0 is undefined. So that denominator, 5 minus x, cannot equal 0. That means if we minus the 5, minus x cannot equal minus 5, or x cannot equal 5. So my domain is all numbers except for 5. I can write that in interval notation as negative infinity to 5, union 5 to infinity, making sure I'm using those parentheses with the 5s to indicate that 5 is not actually part of that domain. So domain is everything except for 5. So notice what happened here is when you take f divided by g, because we cannot divide by 0, your domain is going to contain whenever function g cannot equal 0. All right, we've got one more, g divided by f. So 5 minus x over x squared minus 3x. I'm going to leave that like that. There's not a ton of simplifying we can do. In terms of the domain, once again, we have something to think about. Division by 0 is undefined. So my denominator, which is function f, x squared minus 3x cannot equal 0. I can factor out an x. X squared minus 3x becomes x minus 3. That means either of the factors cannot equal 0. So x cannot equal 0, or x cannot equal 3. So my domain would be all numbers except for 0, except for 3. In interval notation, that's everything from negative infinity to 0, as well as 0 to 3, 3 to infinity. Once again, notice I'm using those parentheses because 0 and 3 are not part of that domain. And the other thing to notice is that my domain considers the fact that function f of x cannot equal 0. If you take g divided by f, that means function f of x cannot equal 0. Once again, that's because division by 0 is undefined. Now, the operation I'd like to focus on with the rest of this video is something called a composition, or composition of functions. A composition of functions is when you take one function and you plug that into another function. So there's two different types of notation we can use. They mean the same thing. So I can write this as f parentheses g of x, f of g of x. Or we can use this little circle to mean composition. So I read this as f composed with g. What this notation means is we start with our input, which is x. We plug that into function g, that gives us g of x. And then this g of x is now our input for function f. We plug that into function f, and that gives us our composition, f composed with g. So let's see how this works with a couple of examples. For the functions x squared minus 3x and g of x equals 2x minus 4, find the following. So let's start with this first one in my list, which is f composed with g. That means we are going to take f of g of x. Or in other words, we're going to take function g and plug that into function f. So f of g of x means we're going to take f of, in this case, 2x minus 4. So I'm going to take function g, which is 2x minus 4, and that gets plugged in for my x's in function f. So this becomes 2x minus 4 squared minus 3 times 2x minus 4. So again, I took function g, which was the 2x minus 4, and that got plugged in for my x's in function f. That is f composed with g. We can simplify this expression. We can multiply out the 2x minus 4 squared. We can use FOIL or recognize the pattern that says when you square a binomial, you'll get first term squared. So 2 squared is 4. So we get 4x squared. And then you do 2x times minus 4 is minus 8x, and you double it. So middle term is minus 16x. And then minus 4 times minus 4 is plus 16. Then I distribute the negative 3. That gives me minus 6x plus 12. Finally, I can combine my like terms. So I've got 4x squared minus 22x plus 28. And there's my final answer. That is F composed with G. Now with compositions, the order matters. If we want to compute G composed with F, that means now we're taking function F and plugging that into function G. So let's see what happens. We'll probably get a different answer. If we take function F and we put it into function G, that means now we're computing G of x squared minus 3x. So now I'm going to take x squared minus 3x, which is function F, and I'm going to put it in for the x in function G. So that gives me 2 times x squared minus 3x, then minus 4. I can simplify by distributing the 2, so 2x squared minus 6x minus 4, and there are no like terms, so that would be my final answer. So the second thing listed is your inside function. That's what you're plugging in to the first function listed. So G composed with F means function F goes into function G. All right, let's do one more. G composed with G. We can compose a function with itself. Let's see what that looks like. So this means we're going to take G of G, or G of 2x minus 4. We're going to take 2x minus 4, and we're going to plug that in for x in function G. So that gives me 2 times 2x minus 4, then minus 4. Or if we distribute 4x minus 8 minus 4, combine like terms, 4x minus 12. So there's another example of a composition. All right, let's run through an example that has some rational functions. Same process, but algebra is going to be a tiny bit more complicated. So now we've got the functions f of x equals x over x minus 4, and g of x equals 2 over x. Let's find f composed with g and g composed with f. So f composed with g means we're going to take function g and plug that into function f. In other words, in this case, we'll be taking f of 2 over x. There we go, f of 2 over x. So I'm going to take my function f and I'm going to replace both of those x's with 2 over x. So now I have this complex fraction, 2 over x divided by 2 over x minus 4. We need to simplify this. We don't want to have fractions within a fraction. And there's a couple different ways you can simplify it. My preferred method of working with complex fractions is to multiply everything by the least common denominator. And so in this case, the only denominator is x. We have an LCD of x. This 4 is technically a 4 over 1. So my LCD is just x. So I'm going to multiply the top and the bottom by x. In other words, I'm multiplying every single term in this expression by x. So let's see what happens when we do that. 2 over x times x, the x's cancel and we're just left with 2. On the bottom, same thing happens with the first term. 2 over x times x, the x's cancel, we're just left with 2. And then minus 4x, minus 4x. And that's my final answer in simplified form, f composed with g. All right, what if we go in the other order? Let's find g composed with f. So now we are taking function f, which is x over x minus 4, and we are plugging that into function g. So I'm going to replace the x in function g with x over x minus 4. So now we've got 2 divided by x over x minus 4. So a couple ways we can simplify this. We could use that same strategy of multiplying everything by the LCD, which in this case would just be x minus 4. But I think what I'm going to do, this problem, technically we have the number 2, and we're dividing it by x minus 4. So I can copy dot flip. So 2, this becomes 2 times the reciprocal. Dividing by a fraction is the same as multiplying by its reciprocal. So now I've got 2 times x minus 4 over x. And I can just multiply straight across. 2 times x minus 4 is 2x minus 8. 1 times x is x. And there's my final answer. 2x minus 8 divided by x. All right, I want to look at one more example of compositions. This example is a little bit different because now we're not given equations. Our functions are given to us in graphical form. But the idea remains the same. If we're finding a composition, we are taking one function and plugging it into the other. So let's see how that works with a graph. First problem says f composed with g at 3. So we're working at x equal 3. And to do this problem, we're going to start with the inside and work our way out. So we're going to start by finding g of 3. What is the output for function g when x is 3? So g of 3, I'm going to go to my graph g. I'm going to find x equal 3 and figure out what the output or the y value is. So x equal 3, the y value is 4, so g of 3 equals 4. So this g of 3 turns into a 4. And now I've got to find f of 4. So again, g of 3 turns into 4. So to finish, we're going to find f of 4. So I'm going to go to my graph of f. X equal 4. When x is 4, the y value is 0. So f of 4 equals 0. And that's going to be my final answer. So with this composition problem, really it's a two-step problem. We find g of 3 first. That gave me 4. Then I find f of 4, and that gives me my final answer. So we start on the inside and work our way out. So f of g of 3 is equal to 0. All right, what about the next one? G of f of 4. So we're going to start on the inside. We're going to find f of 4. And let's see, we actually already did that, but let's do that again. When x is 4, the y value is 0. So f of 4 is 0. This f of 4 turns into a 0. So now I have to find g of 0. So I'm going to go to my graph of g. When x is 0, the y value is 2. And that is my final answer. So again, there were two steps to this problem. I found f of 4 first. That gave me 0. Then I found g of 0 to get an answer of 2. And that is my final answer. All right, that was my last example in this video. As always, please let me know if anything is unclear.